All right, so thanks for the invitation. It's great to be here, especially in the middle of October. This is the best time, so thank you. I will describe a couple of topics, and please stop me as I go and ask questions, and I'll maybe take a little pause in the middle. What I want to talk to you about is how we use quantum mechanics and essentially surrogate of quantum mechanics for designing materials and answering questions of what the atoms are doing on the microscopic scale for device applications such as catalysis and batteries and biomolecular systems and all sorts of other things that are made out of atoms, which is pretty much everything. So we really want to know what happens on that scale. And our goal is really to construct computational digital twins so we can understand using computers to supplement what experiments are doing. Okay, so what we want to do is solve the entire Schrödinger equation on a scale that's relevant to real systems. So this is an example of a catalytic system. Of course, this is impossible. Schrödinger equation is very complicated to solve. So we have to make some approximations along the way, and I'll describe some of those approximations and how we can speed them up using machine learning. Okay, so the first step is, of course, to describe the electronic structure, right? So there are many methods for doing that. They have their pros and cons, and there are new methods coming up that I'll talk about. And once you're done with that, and that's a very big problem, I think that's the biggest problem. Once you're done with that, you can drop it completely to some extent and focus on just the atoms and forget about the electrons. And that gets you a lot of speed in being able to do dynamics, molecular dynamics, essentially at quantum accuracy. That's the method we're working on. And if you can do that, then you also sort of cannot get to the scales that you need necessarily because there are some rare events that usually control the behavior of materials. So you need to do some tricks with statistical methods and enhanced sampling, which I don't think I will have time to talk about, but just to keep you through the entire chain of things. And once you have this acceleration to the relevant timescales, then you can cover both the size and timescales needed to access questions and materials. Okay, so that's the idea. So we have methods that allow us to compute the most important quantity for all this business is the energy, the potential energy as a function of atomic positions. Okay, so that gives you derivatives, which are forces, and that gives you a way to propagate in time and look at what happens in the system. You can compute this with very simple analytical functional forms, these classical potentials for a lot of atoms. You could do this with density functional theory, or you could do this with many-body quantum methods. And sort of the trade-off here is, of course, how accurate you want to be and how much computation time you have. It depends also on the problem. Sometimes these approximations on the left that are sort of fast and not so accurate may not even work. Right? So you have to fall back on the very exact ones. Okay, so but what you can do is also learn from the more expensive methods to construct cheaper methods. And this is where machine learning comes in. So for instance, I'll talk about how we can use first principles computations to design force fields or interatomic potentials that are almost as accurate but much, much, much faster. Or you could design new density functionals for DFT approximations using quantum methods. Again, using machine learning and training data from those higher order calculations. And you can combine these and essentially have a quick model that has sort of the accuracy of some wave function methods. And you can take it further and drop some degrees of freedom and do dimensionality reduction and get coarse graining. And what's interesting, you can also, if you have this pipeline working, you can also, when you run into problems, when your model is trained on some data but does not include some data that it needs to be accurate, you can fall back and generate more data. And if you build the model in such a way that it knows that it doesn't have the data, then you can do what's called active learning and just go down the chain and get more accurate data and retrain your model and adaptively and iteratively improve them and sort of get better at accuracy while still maintaining the high computational efficiency. Okay, so that's the program. So I'll talk about the biggest sort of challenge in the field currently, the density functional theory and how it fails and how to make it better. And then I'll talk about how, based on density functional theory, train interatomic potentials so you can do very large, interesting simulations of materials. And then I'll talk about some additional topics if I have time. Okay, so in all of this, machine learning will essentially be used as a regression tool, so compressing information from expensive calculations down to cheaper calculations and sort of dropping some complexity, of course, like dropping electrons and sort of reducing dimensionality. And essentially, it's a compression tool, right? So that's what we always do. We do sort of experiments, and we try to compress it into theories and models. And in this case, we do experiments on computers using expensive methods, and we compress them into some sort of cheaper models using machine learning. Okay, so what is DFT? How many of you have heard of DFT? Just very quickly. Okay, all right. So anyhow, I won't go into details of what DFT is. That's great. Just to mention, this is a very, very important method. Why we're focusing on it, why we're using it, is because it's, of course, in some of the top papers of all time in terms of citations, and it's also about 40% of all scientific compute. If you look at all the supercomputing centers in the world, in Europe and US, and you see who is running calculations, well, it's mostly DFT. And then there's also smaller parts in Lattice QCD, is I think the second one, and some quantum chemistry, much, much smaller. But it's essentially this, right? And so, and it doesn't work very well for many systems. But people still run it because it's so cheap compared to alternatives, and at the same time gives you predictive accuracy. Okay, so let's see what we can do with that. The unfortunate thing about DFT is that if you try to use it for anything like in real application settings, I used to work in industry and we had all sorts of problems and we couldn't even get reliable answers for catalysis or for batteries or for fuel cells or many, many other things. The sad truth is that it actually gives you qualitative errors on the order of 1 electron volt sometimes for adsorption energies of molecules on surfaces, for reaction energies of lithium coming into your batteries, so if you want to describe your batteries in cell phones and laptops. And this has to do with all sorts of failures of approximations. And the approximations we make in DFT, as you probably know, is we start with essentially solving the many-body Schrödinger equation in density functional theory formalism, which sort of exactly guarantees that there is this sort of charge density as the main object in which you can formulate the theory instead of the many-body wave function. Right, so in principle, you could formulate your whole quantum mechanics using only a single electron charge density, and then represent all the complexity of the quantum many-body interaction using the exchange correlation term, which is basically just a name for hiding everything you don't know explicitly. And then you train that on expensive data from quantum Monte Carlo. That's the LDA approximation. So you just basically take homogeneous electron gas with all the interactions, do exact calculation with quantum Monte Carlo at a couple of densities, and fit a sort of a local approximation, that's LDA. Then you introduce gradient corrections to probe like how electron density maybe varies in space, that's GGA. Then you can introduce second derivatives or kinetic energies, that's meta GGAs. And then, of course, that still doesn't work for many of these systems, and you introduce other orbital dependent correction terms, not correction terms, functional terms, but also sometimes correction terms, but orbital dependent hybrid functionals and things like that. Okay, so there's this sort of ladder of approximations, and it's not a sort of a systematic expansion of terms or in any way variational in this direction. So it's basically a way of fixing issues by putting more terms and then trying to sort of hope that you get higher accuracy. So this is sort of a typical machine learning problem, if you will, right? You start with regressing to something simple, and then you add more terms, more parameters, and you fit that to somehow represent experiment better. RPA is a random phase approximation. Yeah, that's you can go up to sort of many-body methods like that to incorporate some of the correlation once everything else doesn't work. Tau is the kinetic energy density. Yes, it's for the kinetic energy density. Yeah. Mm-hmm. Yep. Okay. All right. So just to very quickly review how DFT is typically implemented. This is the Kohn-Sham DFT procedure. It basically starts with formulating the whole problem in terms of auxiliary set of independent electrons, and then it's just a way of representing the density in the end, because you need to have some sort of representation of the density, and it's quite efficient because you can write down exactly the kinetic energy for independent non-interacting electrons, and once you write down the total electronic density as the sum of the single electron wave functions, you can use that density in your effective potential, which includes the Hartree term. It includes this unknown exchange correlation term and the external potential in which, of course, all the electrons live. Then you can solve your single body Schrödinger equation for each of these independent electrons well, they're not exactly independent, but they're sort of, it's in terms of single electrons, right, this whole representation. And then you get your new orbitals, and these orbitals can be combined to give you new density, and you keep repeating this. And of course, it's all governed by the accuracy of the exchange correlation term. And one thing that you get from inaccurate representation of the exchange correlation is that in this formalism, in the Hartree term, you include electrons that are in your system, but also that becomes the potential in which each electron lives. So it's basically each electron interacts with its own charge density. And that leads to what's called self-interaction error. So in other words, whenever you have a localized system of electrons, so some d electrons or f electrons, the Hartree term, the self-interaction term, is quite big. And so as a result, all the materials that are interesting with correlation, like when you have when you have transition metal oxides or dichlorogenides and things like that, these localized electrons will be problematic because they'll start shifting your energy levels and giving you total energies that are not very accurate. And so this is an issue. So what people do to fix this is either add some ad hoc corrections on each d electron. You put some Hubbard terms to replace what's going wrong with this mean field Hartree kind of self-interaction, or you bring back ideas from Hartree-Fock and you try to get exact exchange to cancel your self-interaction, because if you remember in Hartree-Fock on one electron level, your exact exchange is exactly canceling the self-interaction for one electron, and that's nice. So the idea would be to bring back this exchange integral, which is this quadruple integral in terms of electronic orbitals, and you try to put it into the exchange correlation functional to replace some of this uniform exchange term that you usually use, this expression by Dirac that sort of captures exchange of the uniform electron gas. That's the baseline. So you basically take some of it out and put back some of the exact exchange, which hopefully cancels some of this self-interaction. Okay? Any questions so far? Okay, all right. So this is a typical quantity you would need to compute in your DFT, in your hybrid DFT. This is now called hybrid DFT, right? This is one of those higher rank approximations that is supposed to fix some of the self-interaction business. So this is expensive to compute, and especially when you're using periodic systems where you have a Fourier decomposition of your orbitals, in other words, a plane wave basis set. This becomes a bottleneck in the computation. Okay, so as a sort of practice problem, we asked, well, can we actually deploy machine learning to replace this exact but very expensive integral by something cheaper that still lives in sort of DFT world? And can we learn this exchange energy as a density functional? Okay, so this is not, of course, trivial to write this down as a density functional. In other words, some sort of integral of the density, because it's quite non-local, so you can't really do a local approximation to it like an LDA. So you have to do something different. So what we decided to do is to say, okay, well, can we write it down, of course, in terms of just the density value at each position, the gradient of the density, also kinetic energy density of the electrons, which you can write down as a Laplacian or like second derivative here. And also the density matrix, you can also throw that in. It's not a difficult thing to formulate. And so you have these ingredients, and then out of these ingredients, you can build non-local features. This is what they do in machine learning. You formulate some sort of a representation of your input. These are our input variables, right? So we form some representation, non-local features, and then we build a machine learning model on them, basically a regression model, to get us the value of this exchange energy. Or what we wanted to actually do is to learn exchange correlation, right? This is the biggest, of course, target to improve DFT. So we want to be systematic in sort of learning exchange correlation, and the first step is to try to learn the exchange. Okay. So these non-local features are just some, non-local kernels, and then you stick in your density here. You do some integrals, and then that becomes the basis for machine learning. And what's nice about this approach is that because you're sort of constructing features first and then doing regression on them, you can make sure that the features are constructed in such a way that they satisfy some exact constraints. And you can derive this exact constraint for the exchange energy that if you rescale the density, if you compress the density, then it basically rescales in a certain way the exchange energy. This is something that comes from the integral. Right? So you can build that into the machine learning model so that it doesn't have to learn this exact constraint that physics needs to obey. Okay, Then you can throw in all these other features I talked about and construct a regression model and train it on the reference data, the training data, using exact exchange calculations. These are the expensive ones, right? So we're doing exact expensive calculations and using these features which are cheaper to evaluate than those nasty integrals. We're trying to learn this. And the method that we use is called Gaussian process regression. How many of you have heard of Gaussian process regression? Okay, I guess maybe about a third. Okay, so just very quickly, you start with some sort of a distance metric in your space of inputs. And then this is called a kernel function. And then the idea of Gaussian process regression is that if the points are close in input, most likely they're going to be, the output will be correlated, right? So you form this correlation kind of approach that essentially gives you an estimate for the output at a given input as a weighted sum of these kernel values. So if you're close, the kernel will be large, and so that will be the inputs that you do know on which you train the model, that will be weighted higher in your summation, right? So then you get somehow more contribution, and then you have to learn these weights. Okay, yes?
What kind of kernel do you use? Do you use RBF?
So, yeah, I'll show you. So yeah, we can use RBF. We can use additive kernels. We can, in another problem that I'll describe later, we use inner product kernels. So this is something that one needs to experiment with, and some kernels work better than others. Yeah. Later I'll mention that depending on the structure of the kernel, you can actually, once you do the training, you can accelerate the inference significantly. So this is one downside of Gaussian process regression, already apparent in this formula, is that to do a prediction on some sort of output, you need to do summation of all the things that you know. In other words, you have to loop over the training set every single time you want to do a prediction. So this, if you have a very large training set, that basically becomes very expensive. But in some kernels, you can essentially do the summation first and sort of pre-compute the values for all the training set, and then your evaluation becomes constant time in terms of the number of training points. So that's another consideration when you choose a kernel. It's not only the accuracy, but also how you can computationally improve the inference. Yeah?
Is this similar in spirit with self-attention? Self-attention is also a way to...
I guess in spirit it's similar, right? But in numerical implementation it's very different. So neural networks are a little bit different how you do inference there. Yeah. Yeah. Yes. So okay. So the permutation invariance and equivariance is usually built into the features that you use in the K. Yeah. So so whatever representation you use for representing your inputs this way. Yeah. And then K is some sort of function which could be like a Gaussian functions for it. Yeah.
I think of this as a smoother version of Amy's neighbor.
In a way, yes. Yeah. So basically, yeah, you loop over the neighbors and you pick up contributions from your neighbors to predict something in between. Yeah. Okay. So so we have this Gaussian process, which basically is supposed to predict at each point in space what the contribution to the exchange correlation energy is, and then you sum it over all of space. So this is, for instance, a cloud of electrons, and then you have these points which you pick up contributions from. Then you can compute all these covariances from the kernel functions, and what you train this model on, because you don't have any observables per point in your space there's no sort of observable local decomposition, so you train it on the total energies of molecules from Hartree-Fock calculations, from some quantum chemistry calculations, even from experiment if you want. So these total energy differences, I should say more precisely, that those are used for training this. So you could say, I'm going to take very high order quantum chemistry calculations for energy differences between molecular states, or barrier heights for reactions, or what we commonly use as atomization energies, which are even sometimes maybe experimentally accessible. In other words, how much energy it takes to rip apart a material or a molecule. And we train this model on a very large set of molecules because we want a universal exchange correlation functional. So we do this on both solids and molecules. And we use databases that people have pre-computed with higher quality methods, of course. So there's the cohesive energies of solids. There's this very large database of molecular reaction energy differences. And we add our own points. And this is sort of something that can be systematically improved. You generate more accurate data, and you can augment this database for training purposes. And then when a model is done, it's implemented in either Gaussian type orbital codes like PySCF or plane wave codes like GPAW. And in the future, we'll probably implement in other codes as well. So this is the approach we call CIDR. Okay, so they're very...
What's the dimension of your feature? GP symbol, like going very high dimension.
Yeah, going very high dimension is difficult. So in practice, we typically stick to under 100. Yeah. I mean, it depends. you start with some sort of representation of your atomic system and then train your model on your reference data, which now is a bunch of energies and forces from a quantum calculation. And then you deploy that in the time evolution simulation. Okay, so there are different codes that we developed that allow you to use either Gaussian processes or neural networks for that. Okay, so again, you start by building in as much as possible of physical symmetries into your representation, into the model itself, so it doesn't have to learn things like energy conservation, momentum conservation, and things like that. And so the one way you can do that is by building, of course, invariance with respect to rotations directly into the way you construct your network. That way you have conservative forces, and your model, when you run it, it will respect translational rotational symmetry, so you get momentum and angular momentum conservation and energy conservation. So this is good, right? So basically, you build an invariance with respect to the appropriate symmetry groups, and then you have you don't have to rely on tons of data for the model to learn. Okay, so this is what we put into the training process. Okay, so one thing you could do is build a model out of distances and angles that will be automatically rotationally and translationally invariant. Okay, so but then you have to decide how to exactly do this, at what order of these kind of invariants do you stop? But this is something that you can do systematically. So one first attempt that we were doing in this direction was use what is called the atomic cluster expansion. Is basically a systematic way of writing down any invariant function of atomic positions in terms of spherical harmonics and radial basis functions. It turns out to be a complete basis to represent any sort of 3D structure. And these atomic cluster expansion objects, these spherical harmonics and radial basis functions, you can form them into some sort of a tensor, and then that tensor becomes, and then you can contract some of the indices to get an invariant, and that invariant becomes sort of systematically improvable representation of the 3D structure of your molecule. And then you can use that as a feature for the Gaussian process regression. Okay, so in this case, you basically represent your molecule or your crystal, and you do it for every atom. You look at the neighbors in a certain radial separation distance. This is what we call radial cutoff. And you look at what the neighbors are doing. You look at their positions in space, these vectors. You build these invariants using atomic cluster expansion, and then you construct Gaussian processes on top of that. Right, so just another sort of representation of what the Gaussian process would look like, right? It's a bunch of smooth functions that you try to generate, encouraging them to go through points for which you know the answer, and then they're trying to predict what the answer is, what the value is at points in between. So you're trying to do interpolation from this regression. And one thing you get from Gaussian process regression, to add to what I said before, is because you can draw multiple Gaussians that satisfy sort of this the training set with whatever kernel that you formulate, you can have a spread of answers that is larger for points that are far away from your training set. Right? So in other words, the variance of the prediction is larger if you're far away from the training set. This is nice because what this method allows you to do is quantify uncertainty. So in other words, when you ask a model to predict something, because of the way that Gaussian process is constructed, it will know that the point you're trying to predict, for instance, here, is far away from any training point, and so the uncertainty will be larger. And if it gives you high uncertainty, then you can use that to have the model output at every point in your calculation. If uncertainty is high enough, it will say, I don't know how to predict this, give me more DFT data. And so you know which structure you're trying to predict it for, and you go back and generate that training point on the fly during your simulation, and improve your model as it goes. So it tries to explore whatever dynamics is doing, whatever regions of configuration space the evolution is taking the model. If it knows its own uncertainty at every point, it can improve its training set on the fly, right? So this is active learning. So it can fall back on the quantum method every time it needs to. And for this, it becomes very efficient to use these inner product kernels. Again, because as you keep exploring, your training set grows larger and larger and larger. You don't want your model to become slower and slower and slower. And so for this, for this inner product kernel, you can actually reorder the summation so that for inference, you don't need to loop over the whole training set. So in other words, it becomes a constant cost model, as I mentioned, right? So this is possible for some classes of kernels, but not for all of them. So this is basically becomes a quadratic form once you reorder the indices here in the summation. Okay, so then you can run simulations. This is just an example. This is a catalytic system. This is platinum. This is hydrogen atom. Hydrogen atoms in the surface, in the gas. And what's happening is that they are reacting with the surface. And every time you see a red, that means the model has not seen this data. It's starting from essentially no information whatsoever. This is a nice thing about active learning. You can basically say, this model, I have no idea how to train it. I don't know what the states are that are important. I don't want to guess it. Let it figure it out by itself. So you run with zero knowledge. It starts off by essentially lots of DFT calls. So in the beginning, it calls DFT quite a lot. And then towards the end of the simulation, it basically has learned everything it needs to know. And it needs about 500, maybe about 600 calls to DFT to learn this particular interaction of hydrogen gas with platinum surface. And once it's trained, it actually can predict something that's very close to experiment. Right, so you can actually run it in production mode then and count how many reactions have happened at different temperatures. And then you can do Arrhenius plots of essentially the activation energy for this reaction simply by doing the log of the reactivity with respect to temperature. And you find the activation energy actually matches with what experiments are doing. So you can actually construct a digital twin like that by essentially allowing it automatically to learn from DFT as it needs to on the fly. Okay, so this is the idea. Because in catalysis, it's very difficult to guess what's happening exactly on the surface. And pretty much any reaction system, it's like that. For solid-state reactions, it's even worse. Okay, so and then once you finish your model, you can deploy it because of the sort of the constant cost trick, because of the way you can reorder the kernel calculation at inference time, at prediction time. You freeze your training set. You can deploy a very large calculation. In fact, this is the largest MD simulation ever. It's 1 trillion atoms, and it's running with this model under the hood on the Frontier machine. This is the largest sort of GPU machine we have in the US right now. So it's taking over the entire machine, and it's running this calculation of platinum hydrogen. You could use it also for figuring out how catalysts form. So you, as an application, you can look at, for instance, what happens when you experimentally take a silver substrate and you put palladium islands on it and you anneal. And what we see in simulation exactly matches what they see in experiment, but they didn't know why this was happening, is there's this etching of silver from the first layer and fattening and increasing the thickness of these palladium islands. And they become all of a sudden very good catalysts. So this is revealed by the MD simulation run with this method, is that palladium actually gets mixed in a 50-50 or so ratio in these islands. They basically suck in this silver, and then they become 2 stories instead of 1 story high, and then they become this sort of magic combination of activity and selectivity, reactivity and selectivity for hydrogenation reactions. So it's kind of nice that you are able to explain that this can happen already at the temperature that they are running the experiment, about 500 Kelvin, but this happens in about 2 microseconds. And this is what they could never see in experiment because STM tips take minutes to scan samples, but this process is revealed by these simulations. Okay, maybe I'll skip the introduction to neural networks. I'll just show you very quickly a different class of models that we've developed for representing energies of atomic systems. And the idea here is, well, we tried to guess the representation. We did this in the Gaussian processes for exchange correlation functionals. We tried to construct these features. We also tried to construct these features out of atomic cluster expansions of various orders when we tried to do this Gaussian process in the previous example. But what if you don't want to even bother with feature selection? And this is sort of where deep learning has taken us, right? So this is this idea that, let the model figure it out on its own, let it learn its own representation that it needs. So this is the idea of deep learning applied to atomic systems. The first was work called SNET, that essentially said, okay, well, let's allow atoms to pass messages to each other, and let's basically have a neural network that agglomerates information from all the neighbors, figures out its own feature, and then passes that feature to the nearest neighbors as well. And so this sort of very flexible framework of what's called message passing neural net or graph neural net was formulated, and distance information to your nearest neighbors was being passed around. It was quite successful, but what became apparent when we did some testing is that distances alone are not sufficient. There are certain cases where you also need to know the direction of your atomic neighbors. And so that becomes more difficult because direction is not necessarily just a number, so you can't easily put it into a neural network. Neural networks are usually like, you take numbers, you multiply them, and you add some shift, and then you pass it through a nonlinear function, and then you do this many, many, many times, and you get good regression capabilities. But when you deal with vectors, it's no longer so simple. So this is where we started looking at what does it take to make an equivariant model? An equivariant model essentially operates on vectors and tensors, and these are now objects that have some rotational character. They're just not numbers, not just numbers, right? So if you take your system of atoms and you rotate it, the feature itself needs to rotate because it's a vector now, or a tensor. Like it has to transform according to whatever you're doing it in 3D space. It cannot just stay a number and be an invariant forever, right? So if you go too early to this internal representation as an invariant, like using distances and angles, you necessarily lose some of the information. So the idea of equivariant neural nets is essentially not to try to go to an invariant until the very end. So keep the representation equivariant, in other words, allow it to transform according to whatever symmetry group of rotations or translations that you have. And so your internal representation inside the network and all the operations inside the network have to respect this rotational equivariance. In other words, whatever happens in the network essentially commutes with rotation operations. So this is rotational equivariance. And so what you have to do for that is to build it out of tensor products. So you essentially try to see what operations are allowed so that equivariance is preserved, so that at every step in the network something non-trivial happens. Information is being passed around, which encodes directional information between the atoms, but at the same time, it exactly preserves the rotational equivariance. And so after everything is done, towards the end, at the end of the network, you basically just take the scalar invariant, which is the energy. Okay, but then sort of all the directional information is still in the representation. So this is a model called NEQUIP that was created, and yeah, just some example, like you could do cross products as an example of a very simple equivariance. A cross product is an operation on vectors, which gives you another vector. It's more information captured than just a dot product, for instance, which takes two vectors and produces just a scalar. So we include all the sort of invariants as well as those equivariant objects up to whatever rotation order in the spherical harmonics that you want, and then increases your sort of angular resolution, if you will, for the rotational information. The outcome was quite spectacular. What we found is that the models, once they're allowed to do equivariant operations in the representation, they essentially learn on a different scaling law, right? So their learning capability changes. The exponent of the scaling of how much the error decreases with the amount of the training set size on the log scale dramatically shifts. And if we've seen this from many examples, and people have reproduced this now many times, we don't really understand exactly why it happens, as is normal in deep learning these days. But you do see empirically that the model needs far less data to learn, and it learns much more accurately. You could explain it by saying, well, okay, the representation is sort of is somehow more aware of directional character and geometry, but it's unclear how exactly this happens and why. Anyhow, so this is essentially the state of the art these days. These equivariant models, and you can build them using message passing formalism, or you could constrain information. In other words, atoms share information within a certain restricted neighborhood. There's advantages numerically to doing this as opposed to just letting the atoms all communicate by a large graph. The advantage is in parallelization of these methods, right? it's been difficult to parallelize this kind of calculation because you need to keep around a very, very long list of your neighbors in your calculation. That makes it very difficult to deploy on multiple GPUs. Instead, if you contain information in a certain region, then every atom has a certain region to deal with, and then you can parallelize over atoms much more easily. So this is what we could try to do, and this is an example of this equivariant neural network that is running a blood clotting protein in explicit water, 100 million atoms on about 5,000 GPUs because of this ability to parallelize on each atom and do this sort of equivariant calculation on each atom separately. So this is what's called the Allegro model. And you can do all sorts of applications to catalysis as well and look at how deactivation of catalysts happen. So we always try to somehow do some applications with these methods to demonstrate that they work or don't work. And maybe very quickly, I'll show you. I'll show you this sort of where everything is going nowadays. People have gotten so excited by these large deep neural nets and followed this sort of ChatGPT kind of single model can learn the entire internet approach that they basically asked, well, can we have a single NeQuip model or single equivariant neural network learn the entire inorganic space? So in other words, do DFT calculations on all known crystals and molecules and learn a single model that basically becomes your replacement for DFT. And so this is a very interesting sort of development in the past 2 years. The first example was by Google. They made this genome model, which essentially took NeQuip, reimplemented it in JAX, and trained it on all crystals, and they achieved some very interesting results. There have been many other attempts since then, where we generalized this NeQuip model to include some of these ACE features also. Then Gabor Jani has taken this idea and implemented MACE. And Grace was recently developed. So all these models essentially trying to use the same kind of architecture of the equivariant neural network, but now train it on all of the known inorganic world of crystals. And so the labels there become energies and forces in pretty much everything that we've ever seen and computed. And you sort of just rely on the scaling ability of neural nets to get this one model that can do everything. So this is somehow a competition, and there's this leaderboard of benchmarks that every couple of months people put new models in there and train them on bigger data. So it's quite interesting. It's very computer science-like. Interestingly, the best performing models, the top performing models, they're all these equivariant neural networks, which is essentially, I think, really plateaued in terms of accuracy, right? So these best models, the two best models right now, are variants of the same thing. The original NeQuip is doing almost as well as the best model out there. And this is an average accuracy. So there will be lots of cases, and we know this for sure, that this model does not describe. And we cannot make these models much better. Right. So at this point, the field has somehow reached a question like, what other architectures should we be exploring for these models? Because these are somehow plateaued in their capability. Anyhow, this is very interesting. Like, can we do better than this, or are we pretty much done? This is unclear. There's probably some interesting ideas out there, but this also raises a question like, how good can you expect a single neural network model to be in covering all of inorganic and organic space? Like, can it ever be as good as DFT? Right? Well, then probably it's going to get very, very, very expensive. Right. So this is the question. Like, these super expensive foundation models, as they call them, that are not also great everywhere. They're generating quite a lot of excitement because you could do very quick calculations now, much, much quicker, like millions of times quicker than any DFT, and very quickly answer some questions about materials and maybe do some sampling of structures. But of course, they're not going to give you the super high accuracy of quantum methods, at least not just yet. Okay, so if you're interested in this, we just came out with a much faster way of training these models, so you can get one of these foundation models in a day, essentially. If you are in this business, if you want to try out some of these new NeQuip infrastructure capabilities, there is also inference on the inference speedups that were achieved by incorporating some of these tools from the computer science community and from the industry. So the speed is something that we're essentially mostly concerned with, is how to make these models much, much faster. So that, because in the end, what we want to deploy them for is molecular dynamics, which means taking billions of time steps and repeating it over and over and over. So a lot of engineering effort has gone into making these things faster, right? So we've so far in the past few months we've taken it up to 20 times faster. Yeah.
If you're going to train one model once and for all, why do we care about how quickly you can train? You're not going to be training every day, right?
Well, it's because it was so difficult to do. It took months. So you cannot iterate with architectures and training sets quickly if each model takes weeks or months to train. So if you can parallelize the training in the way that you can get an answer in a day, then you can start answering questions like how far can we push the accuracy of these foundation models. It's just a practical thing. But right now we don't know what it takes to train a good model. They're all sort of okay-ish. And now we need to iterate with architectures and ideas. Speed is helpful.
When would you know to stop?
When does the model stop training?
Yeah.
Yeah, so this is,
Improving architecture. You can, so if it was taking 3 months, and there are only so many 3 months in a life of a student.
yeah, well, right. So I mean, the typical thing in deep
So now you get 12 hours.
Yeah.
Maybe you're training every day. Maybe, I don't know, when do we stop?
Yeah, that's a very good question. I don't know what is the exact answer for that, right? So you run the training, and you observe the learning rates, and you observe the errors, and essentially you stop in some sort of a practical way, right?
When to stop a single training?
Yeah.
Right? When do you stop the exercise of training, tweak the model, try new architecture?
Oh, yeah, that's,
Right? That cycle.
yeah, I don't know. Yeah, well, I guess when you get to the top of the leaderboard, right? Yeah. Right, exactly. That's a question. Like, you're trying to compress a very complicated data set into a single model, basically like a few million weights. And you're trying to squeeze it down. Like, what we're after actually is the cheapest possible foundation model, because it's not going to be accurate, but it better be very fast. So the question right now is, how small can you make this model to still capture all of an organic and organic complexity? It's an interesting question. Like, how small can you make a chatbot so that you can run it on your cell phone, right? So these kind of questions. Like, so you keep making improvements and making things cheaper. Otherwise, it just costs money to run them every single time. Yeah.
If that's the case, shouldn't you start maybe with the smallest model possible, and then see at which point it converges to a behavior that's appropriate?
Yeah, I mean, there's definitely many ways of doing that, right? So what people have targeted so far is make the model as large as possible, because this is what, again, in the large language model world has been seen, right? You make a model of billions of parameters, and all of a sudden it has some sort of hints of intelligence, or who knows what, right? So you make the model large, you train it in a large amount of data, and its generalizability somehow is qualitatively better. And to some extent, that has been seen also in this as well, right? You make the models large. Initially, the models were very large. Like the Google model is, I think, 60 million weights. I don't remember exactly. But right now, we're just playing with a few million. And right now, I think even getting reasonable models with, let's say, 200,000 weights. So we're trying to sort of squeeze it, knowing now that we can hit a certain accuracy. Now you see how far behind smaller models can be and still be much smaller. So you could do it either way, yeah. I'm probably out of time, but I'm happy to keep going. I don't know. Anyhow, I think it's probably a good time to stop. I'll just want to thank the students and the funding sources. And thank you for your attention.
Thank you so much for a very stimulating talk. And we already have a lot of questions, but if you guys have any quick questions.
How about the size of the implication scales with the size of the molecular?
So in the approximation that I showed, so every atom has a neighborhood in which it has to basically collect information on geometry and come up with its own contribution to the total energy. So that scales linearly. because every atom has a finite distance of information to deal with, right? So what that explicitly omits is any sort of long-range interactions. So what we don't include in these simulations, that's an active area of research of how to do it efficiently, is electrostatic long-range interactions. We find that they're very rarely important to include because they're already captured sufficiently, let's say within 10 to, basically within 10 angstroms. If that's already in the training data, the model learns enough to be pretty good. But there are some cases where electrostatics are important, in which case it will not scale linearly. It will scale like whatever the Ewald summation or fast multiple methods.
So if you have no other question, let's send the
Thank you.